Now we're going to look at, actually go back to the third edition of Royden and Fitzpatrick. It was just Royden in those days. And we're going to look at the construction of a non-measurable set. Section 2.6, this is also in section 2.6 of the fourth edition. I really like the fourth edition, but I really like this section 2.6 stuff maybe a little bit better than what they've done in the fourth edition. I think this is a little more tangible as far as this kind of material can be tangible. This includes maybe my favorite, it's certainly the weirdest result in the whole real analysis one, experience. So we're going to construct quote unquote, more details on that shortly. We're going to construct a non-measurable set. We know that the Lebesgue measurable sets form a sigma algebra. We've alleged that that sigma algebra doesn't equal the power set of the reals, that there are non-measurable sets. There are sets on which Lebesgue measure isn't defined. So this is the first time we're hands-on addressing that. Other concerns might be, well, how many non-measurable sets are there? And we'll address that in a supplement as well. And how many measurable sets are there? Are half of the sets measurable? Does that question make any sense? We'll look at some cardinality results in the supplement also. Okay, but the plan here is to construct, quote unquote, a non-measurable set. Okay, we're going to define, I'm going to read this as circle plus. For x and y in the interval from 0 to 1, including 0, excluding 1, define x circle plus y simply as x plus y, if x plus y is less than 1, and x plus y minus 1, if x plus y is greater than or equal to 1. You might think of this sort of like mod 1 arithmetic. So when I add two elements of this interval together and the sum is in the interval, no problem. We'll take that to be the circle plus sum. When I add two numbers in this interval together and it lies outside the interval 0, 1, we'll drag it back 1 unit. And then we will have something in the interval 0, 1. So this circle plus operation takes points, numbers, in the interval 0, 1 as indicated, and gives out other numbers in the interval 0, 1 as indicated, including 0, excluding 1. Just like arithmetic, mod 1. Okay, we need a preliminary lemma, and that is if we take any subset of the interval 0, 1 as given, which is measurable, then for any y in the interval 0, 1, e circle plus y is measurable, and the measure of e circle plus y equals the measure of e. So what we're showing here is that measure is circle plus invariant on measurable subsets of the interval 0, 1. Okay, there's a good deal of geometry behind what's happening here. When I circle plus translate a set, we haven't formally defined that, but of course you circle plus translate each of the elements of that set. We're starting with a subset of the interval 0, 1. Y itself is an interval, is in the interval 0 to 1. So the circle plus sum is defined by this. So what we'll do is we'll take this set E and translate it, regular translate it by an amount Y. But if some of it then lies outside the interval 0, 1, we'll cut that part off and shift it back 1 unit, because that's what we do when you get sums greater than or equal to 1. So we'll actually take set E and break it into two pieces. Let's do that. Okay, so we'll take set E as given, break it into two pieces. We've got a translation of one piece. We've taken the other piece and cut it off and translated it, which is effectively a translation of the other piece. Okay. So we'll define E sub 1 to be E intersect, the interval from 0 to 1 minus y, and E sub 2 to be the rest of set E. E intersect the interval from 1 to y to 1. We've included the 1 minus y in the the E sub 2 stuff and not in the E sub 1 stuff. So what we've done is taken set E and cut it into two pieces. Cutting it at 1 minus y as indicated. Why at 1 minus y? Because we're going to add y to each of these two pieces. When you do so, this piece will contain numbers between y and 1. When I add 1, we'll get numbers between y and 1. They're subsets of the interval 0 to 1, and they won't have to be moved back. This is the part that has to be moved back. When I add y to numbers in this interval, we get out things between 1 and 1 plus y, things bigger than or equal to 1. Okay, that's the part you're going to have to cut off and translate back by 1 unit. So that's why we want to take set E and break it into these two pieces. The pieces are disjoint. They union to give set E, and they're both measurable. Why is that E1 and E2 are both measurable? Because E is measurable, that's hypotheses, and all intervals are measurable, as we've shown. And we're in a sigma algebra, so intersections of measurable sets are measurable. So yeah, E1 and E2 are both measurable. The measure of E being written ultimately here is a disjoint union of E1 and E2. The disjointness is given by this. Then the measure of E is the measure of E1 plus the measure of E2. That's just additivity. When we take E1 and circle plus translate it by an amount y, that simply gives us E1 plus y, as mentioned earlier. We don't get numbers in E1 when we add y. We don't get numbers greater than or equal to 1, so we don't have to adjust it. E1 circle plus y simply is E1 plus y, so that's measurable. The translate of a measurable set is measurable, so E1 plus y is measurable, so E1 circle plus y is measurable. Also, the translate of a set is the same as a set itself. Measure is translation invariant, outer measure is translation invariant, and measure is outer measure restricted to Lebesgue measurable sets. So the measure of E1 circle plus y is the same as the measure of E1 plus y is the same as the measure of E1. So it's looking like measure is circle plus translate invariant so far, but we're only halfway there. We need to look at the other piece, and that's just a translate as well. E2 circle plus y, that would be E2 plus y. That'd be the regular translation. But remember, from the choice of E2, all of those E2 plus y's are greater than or equal to 1. Okay. Then by the definition of circle plus, you'll subtract 1 from all of those. So what we're really doing is taking set E2 and translating it by an amount y minus 1. Well, that's just a translation. So E2 is measurable, as was E1. E2 circle plus y is measurable. And it has the same measure as E2 has, since we've written it as a translation. Okay. Now, E circle plus y is E1 circle plus y, union E2 circle plus y. These are disjoint as well. We can view them as subsets of disjoint intervals. Right? E1 circle plus y is a subset of the interval from y to 1, whereas E2 circle plus y is an element of the interval 0 to y, I think it is. We'll add y and then subtract 1. Yeah, I think that's what we get out of that. So we do have the disjointness. We've written E circle plus y as a union of two measurable sets. We commented a few lines ago that both of these are measurable. So E circle plus y is measurable. And we've got countability on measurable sets. So the measure of E circle plus y is the sum of the measures of these disjoint pieces. We saw the measures of these disjoint pieces were equal to the measures of the untranslated parts, the E1 and the E2. And we observed upstairs that the measure of E1 plus the measure of E2 equals the measure of E. So the measure of E circle plus y equals the measure of E. So indeed, measure is circle plus translate invariant. Of course, it's the way we set things up. It's very localized, right? We're taking subsets of the interval 0, 1, and the parameter y had to be from the interval 0, 1. But we've established circle plus translation invariance of measure as well. Okay, we're going to set up an equivalence relation. We're going to look at representatives from the equivalence classes of that equivalence relation, and then we're going to throw the axiom of choice at this thing. And that's how we're going to create a non-measurable set. All right. So take any two numbers, x and y, in the interval 0, 1. X and y are said to be rationally equivalent if their difference is rational. So two numbers in the interval 0, 1 are rationally equivalent if their difference is rational. That's an equivalence relation on this set, this interval 0 to 1. Of course, it's reflexive and symmetric and should be pretty plausible that it's transitive as well. There's a little something to show there, I suppose. But this does determine an equivalence relation. And one of the main reasons you take an interest in equivalence relations is they produce equivalence classes which partition the set on which they're defined. So this equivalence relation, rational equivalence, will define an equivalence relation on the interval 0, 1, and hence will partition the interval 0, 1 into equivalence classes. We'll probably delve into this in a little detail later. FYI, there are an uncountable number of equivalence classes. That has an impact on how we're going to use those equivalence classes. But we've got an equivalence relation. We've got equivalence classes that partition the interval 0, 1. Excellent. Recall that. Okay, going back talking about the leading into the axiom of choice. I have a supplement prepared on the axiom of choice, best viewed before you get into this stuff. We'll define for F a non-empty family of non-empty sets, which is what we have with this family of equivalence classes. A choice function, lowercase f, on this collection, calligraphy f, is a function, lowercase f, from the family to the union of all the elements of that family with the property that each set f in the family, we have lowercase f of f is a member of the family. All right, so here's what all that stuff means. So we've got a whole bunch of non-empty sets. A choice function simply reaches into any of those sets and picks kind of a representative of that set, picks an element of that set. That's what it means when it says lowercase f of capital F is a member of F. Lowercase f is the function that has chosen an element of set F from this family, calligraphy F of sets. For us, the sets are the equivalence classes, the family, calligraphy F is the collection of all those equivalence classes. So we're going to go through with a choice function and simply pick a representative from each equivalence class. We've got non-empty sets. The equivalence classes are non-empty. In fact, they're even disjoint. Equivalence classes are disjoint, as you know from your background knowledge on equivalence relations. We just need to make sure that a choice function actually exists on this collection of equivalence classes. Okay, a little example, a very little example. Let calligraphy F be the set of sets A, B, and C, where set E has the elements 0, 1, and 2, set B has the elements red, blue, and green, and set C has the elements truth, beauty, and love. An example of a choice function would be to pick an element of set A, say 0, pick an element of set B, say blue, and pick an element of set C, say love. So choice functions simply pick representatives of sets, as it were, elements of sets. Looks like a pretty uncontroversial thing. but the problem is the choice function may not be defined. In the following, we're going to say in the axiom of choice that for any non-empty collection of non-empty sets, a choice function exists. Up here, no problem. These were small finite sets. Where we are and what we're doing, those equivalence classes are fairly nebulous as to what's in them and what isn't. But the axiom of choice allows you to create a set. It's really about the creation of a certain kind of set that includes a representative from each of the sets in this non-empty collection. It doesn't tell you how. That's what I mean by saying it's not defined. The choice function isn't necessarily defined. We merely know a choice function exists. So it's rather arguable as to whether what we're doing actually is a construction because we're leaning on the axiom of choice. It guarantees the existence of this set, but it doesn't tell us how to make this set. The axiom of choice guarantees the existence of a choice function, but it doesn't say how the choice function is to be defined. For this reason, among some others, including some weird applications, really this application that we're in the middle of now, the creation of a non-measurable set, some mathematicians reject the axiom of choice. But at least everybody, they use the axiom of choice. You want to point out, if you use the axiom of choice in a proof, that you want to indicate that you've done so. When using the axiom of choice, clearly make note that you're using the axiom of choice. We're going to use the axiom of choice in the following quote-unquote construction. So why the quote marks? Because we're going to claim the existence of a set. And because we've used the axiom of choice to create that set, we're not going to have any idea what's in that set. It's going to be a subset of the interval 0 to 1, but beyond that, I have no clue what's in that set. So construction, well, its existence is guaranteed by the axiom of choice. All right. By the axiom of choice, there exists a representative of each equivalence class of that equivalence relation, rational equivalence, that we introduced above. We partition the interval 0, 1 into these equivalence classes using that rational equivalence relation. So we're going to define set P to be the set consisting of exactly one representative from each equivalence class. The exactly one stuff wasn't in what we had upstairs, but neither was disjointness from what we had upstairs. But we do have disjointness, so by taking one representative from each set, an element from each equivalence class. Since the equivalence classes are disjoint, we won't repeat representatives. We won't repeat the elements. So set P is defined using the axiom of choice, picking representatives from those equivalence classes. You tell me anything about set P. How about this? It contains exactly one rational number between 0 and 1. All rational numbers have a difference that's rational. So under rational equivalence, maybe extended even to the whole real line, rational equivalence would say any two rational numbers are equivalent. So that's one of the equivalence classes is the rational numbers in the interval 0 to 1. The axiom of choice will guarantee a choice function that picks one of those rational numbers. Okay, so there's one rational number in P, exactly one, in fact. All the other entries are irrational. What's your favorite irrational number between 0 and 1? Square root of 2 over 2. 1 over the square root of 2. It pops up in trig functions. It's between 0 and 1. It's got a square root of 2 in it. It's irrational. Is the square root of 2 over 2 in set P? I don't know, but I know this. Some equivalence class contains a square root of 2 over 2. What's the other stuff in that equivalence class? It's be everything that differs from the square root of 2 over 2 by a rational number. So I'd take the square root of 2 over 2 and I'd add all rational numbers to it and then keep those that lie in the interval 0 to 1. That would be one of the equivalence classes. It would be the equivalence class containing square root of 2 over 2. So what's a second element of P? Well, it's the square root of 2 over 2, circle plus some rational number. That's one of them. All those other numbers in that equivalence class, they're all irrational as well. Which one did you pick? I don't know. That's the problem in using the axiom of choice. So I got a real nebulous understanding of what's inside set P because we use the axiom of choice. But that's how set P is constructed, and its existence is guaranteed by the axiom of choice. We're going to show set P is not measurable. That is, P is not an element of the sigma algebra of Lebesgue measurable sets, and we're going to show this by contradiction. Theorem 2.6.b simply says set P, so constructed, quote unquote, is not measurable. Okay. All right. Let's go through a proof of that. It's actually not too lengthy. First, we need to establish some set theoretic results. How we're going to use set P to create a whole bunch of sets. We're going to partition the interval 0, 1 into some pieces. Let R sub I equals 0 to infinity be an enumeration of the rational numbers in the interval 0 to 1. Choose R sub 0 to equal 0. It's a rational number in that interval. Just pick it as R sub 0. This is a countable collection. It's an infinite subset of the rational numbers between 0 and 1, excluding 1. So enumerate them, denote them as R sub I, where R ranges from 0 to infinity. Treat them as a sequence. We're going to define a collection of sets, a countable collection of sets. Define P sub I to be set P, as defined above using the axiom of choice, circle plus rational number R sub I. So when I equals 0, we're taking P circle plus 0. We're just getting set P out. All right. So we'll do this for I equals 0 to infinity, all the natural numbers with 0 thrown in. So we're creating a countable collection of sets, P sub I. We're about to show the P sub I's partition the interval 0, 1 into a countable collection of disjoint sets. Okay, so we're no longer talking that equivalence class stuff. We've used that. We're moving on to something different. So here we'll have ultimately a countable collection of these P sub I's. Back there we had those equivalence classes, and I claimed the number of equivalence classes was uncountable. So here we will have a countable collection. All right. Suppose X is in both P sub I and P sub J. Then X equals, what do the elements of P sub I look like? They would be an element of P, circle plus, P sub I, circle plus rational number R sub I. So X would be P sub I, circle plus R sub I, where P sub I is some element of set P. X being in P sub J would be some other element of P, presumably, P sub J, call it, circle plus R sub J. What does P sub J look like? P sub J is set P, circle plus R sub J, the jth rational number and that enumeration of it. So if X is in both of those sets, then it can be written in both of these forms, where the P sub I's and the P sub J's are some numbers from set P. Which ones? Well, I don't even know what's in set P very well, so that's not a very useful thing to inquire, which P sub I's and P sub J's. They're elements of set P. Now what we're going to do is show that P sub I and P sub J differ by a rational. Consider this. I'm going to rearrange this equation, maybe it's best to think in terms of, hey, we're doing mod 1 arithmetic with this circle plus stuff. What we do is get p sub I circle plus the additive inverse of p sub j, well, negative p sub j, and r sub j circle plus negative r sub I. So taking the r sub I to the other side and the p sub j to the other side of the equation. This is happening under circle plus addition, so it's maybe not entirely immediately obvious that these are equalities. Think arithmetic mod 1, and it should make sense. Then it should be legitimate for me to, add the same thing to both sides, mod 1. But what we've got over here is a circle plus sum or difference of two rational numbers, and that's going to be rational. So p sub I and p sub j, they differ by a rational. That means they're rationally equivalent. If they're rationally equivalent, p sub I and p sub j, they're from the same equivalence class under tilde. P contains only one representative from each equivalence class. These are from the same equivalence class. Then these must be equal. P sub I must equal p sub j, I must equal j, and capital P sub I must equal capital P sub j. So the only time these P sub I things that we defined intersect is when they're the same. So P sub I intersect P sub j, that's the empty set if I is not equal to j, and they're equal if I equals j. So the P sub i's are disjoint, and they union to give a subset of the interval 0, 1. Okay, union them up, we get a subset of the interval 0, 1. We know they're disjoint, so we got that going on. Do they equal everything in the interval 0, 1? Let's establish that. So we're going to draw a conclusion of equality from this with one more argument. Let's recycle that variable x. Let x be anything between 0 and 1. It's in some equivalence class under rational equivalence. Call it e sub x. Let p sub x be the element of p that is the representative of that set, that class, e sub x. In terms of the choice function, we're saying f of set e sub x is this element, p sub x. P sub x is the choice from this set that has been put into set P, capital P. All right. Well, now we've got x and p sub x from the same equivalence class. So we know p sub x, this representative, circle plus some rational number equals x. That's how we dealt with the equivalence classes. P sub x and x differ by a rational number. Call that rational number q and work mod 1. So there's some rational number q such that p sub x circle plus q equals this x. So x is an element of the union of set p plus q sub I, or plus q, I should say, where we've taken the q to be some particular rational number. I should call it p sub I. I wish I had a p sub I there. But we've got then x in this set. This set is the union of the p sub i's that we had above. So we've shown the x is in some particular p sub I. It's the one corresponding to this rational number q and this representative p sub x. So that gives us x as an element of the union. It was an arbitrary element of the interval 0, 1. So we must have equality. We must have that the union of the p sub i's equals the interval 0, 1. Okay, some weird mod 1 arithmetic stuff and just some set theoretic arguments. Here's the big picture. We've taken the interval 0, 1, broke it into a countable disjoint collection of pieces, p sub I. These pieces, we've got the equipment behind us to say these pieces, these p sub i's, they're measurable. So we'll ask the question, this is going under the assumption that p is measurable. We'll get the p sub i's to be measurable, and that'll lead to a contradiction. So here we go. Assume p is measurable. Now the p sub i's were circle plus translations of set p. If p is measurable, then all the p sub i's are measurable. Also, the measures of the piece of i's is the same as a measure of p. That's what we showed in that first lemma. Now, under the assumption that p is measurable, we've taken the interval 0, 1 and broke it in to a countably infinite number of pieces, all of the same size. And that's a problem. All right, we get 1 as the measure of the interval from 0 to 1. Intervals are measurable and their measures their lengths. That's what we're quoting for those propositions. We've taken the interval 0, 1, it's given, and written it as this disjoint union. Union from I equals 1 to infinity, the piece of i's. We had the union established before. No problems there. We've assumed p is measurable, which gives us, under the assumption, effectively, that all the piece of i's are measurable. Okay, then we've got a measure of a disjoint union of measurable sets. That's the sum of the measures. That's countable additivity, under the assumption that we do have measurability. We don't. So we'll get the sum from I equals 1 to infinity, the measures of the piece of i's. But all the piece of i's had the same measure. They were the measure of set p. So we get the sum from 1 to infinity of the measure of set p. What's a measure of set p? If it's 0, then we've got a series that is 0 plus 0 plus 0 that sums to 0. If it's positive, then we've got the same little positive number repeated infinitely many times in a series, and that diverges to infinity. Same size, countable number, causing a problem. So we get this sum, this series, to be either 0 if the measure of set p equals 0, or we get infinity if the measure of set p is greater than 0. And that's the only choices if p is measurable. That's a contradiction because 1 doesn't equal 0, nor does it equal infinity. There's a contradiction. The assumption we made right here that p is measurable must be false. So p is not measurable. So we don't have a measurable set. Suppose I used the outer measure then. Where do things change? Right here. We'd have to use subadditivity if we address this with outer measure. We'd use subadditivity. We'd pick a less than or equal to up there, and you'd get an infinity out down here. If the measure of p, if the outer measure of p equals 0, then p is measurable. We just showed it isn't. So if we looked at this from the perspective of outer measure, replace all the m's with m stars, we'd have to use subadditivity here, less than or equal to, and we get an infinity down there. Drawing the conclusion 1 is less than or equal to infinity, which that's the case. But with measure, we get to use countable additivity, and that's where the contradiction comes from. So this set p is not measurable. All right, so the big idea was, one more time, we got these piece of i's, countable number of them. We went to some weird lengths to make that a countable collection. Countable collection, disjoint sets, all of the same size. They are all of the same outer measure. Outer measure's translation invariant. It's plus star translation invariant as well, or circle plus, circle plus translation invariant. But we've got a countable collection of sets, all the same size, which partitions the interval 0 to 1. We got a contradiction. It couldn't have measure p equal to 0, or countable additivity would tell us the interval 0, 1 has measure 0. Doesn't, it has measure 1 because it's an interval. Couldn't have positive measure because then that would make the measure of the interval 0, 1 equal to infinity. That's how the contradiction arose. This idea of taking a set and breaking it into a countable number of pieces, all of the same size, can lead to some problems if you want the sum of the pieces to equal the measure of the big piece, the whole thing, the union. If they're all the same size, either they're measure 0 and the whole thing is measure 0, or they're positive measure and the whole thing must have infinite measure. We were trying to get out a measure of 1, so that's where we got the contradiction. I am no real analyst, I am no measure theorist, but I have one little paper, Translation Invariance and Finite Additivity and a Probability Measure on the Natural Numbers. published many years ago, actually with the chair of the department. Not chair in those days. A humble little work. You can click here and access it, but I'm basing it on some similar ideas. You can't put a translation invariant, countably additive measure on the natural numbers. I can't say, suppose every natural number has the same probability, pick a natural number at random. It sounds like a reasonable thing, but what's the probability of each natural number? If it's 0, we got countable additivity, then the whole sample space would have probability 0. And that's not how sample spaces work. Okay, suppose the probability of all the natural numbers, the probability is the same for choosing any one, and that probability is positive. Well, then it's going to diverge by countable additivity. So suppose we dump countable additivity and require finite additivity. Well, some things can be done, enough of that. But the concept in that little paper is actually the same as the concept that we had here in the non-measurability of that set P. Philosophical note, we've used the axiom of choice to create P. We had no idea what set P looks like. I've been big on what does this set look like? I know what an open set of real numbers looks like. I know what a G delta and an F sigma set look like in some sense. I know what a G delta sigma set looks like in a very crude sense, but I've got something. What's a set P look like? No idea. Is 1/2 in set P? I don't know. There's one rational number in set P, but I don't know which one it is because I use the axiom of choice to pick these things. Here's an interesting question, I think. What's the outer measure of set P? It can't be 0 or P would be measurable. And we just showed P is not measurable. So it must have some positive outer measure. Well, what is that positive outer measure? Well, I don't know how this choice function has created set P. I know this, the outer measure of P is strictly greater than 0. Monotonicity, it's a subset of the interval 0, 1, tells me set P has outer measure less than or equal to 1. So I know the measures between 0 and 1. That's about all I got. I don't want to delve into too many details, but you give me an epsilon greater than 0, and I bet you I could make the outer measure of P less than epsilon by having the choice function behave in a certain way. We can make these outer measures small. You can't make it 0, but I bet I can make it small. I bet I can make it close to 1 as well. I don't think I can make it equal to 1. I'd have to think on that. I should watch my words because this is strange stuff and it's easy to make mistakes. But there's a real nebulosity about how set P is defined. It's a reasonable question to ask what's its outer measure. Well, that's I don't think you can determine that because set P isn't very well determined. It has an outer measure, but I don't know what it is well enough to have any clue what that outer measure is. In fact, I think I could probably make it anything between 0 and 1, excluding the endpoints at least. This is another reason you get some objections from the mathematical community for using the axiom of choice. It guaranteed the existence of this thing. It didn't tell us in a realistically constructive way how this set P was created. It merely guarantees its existence. And that left it with a pretty nebulous set of properties. All right, this is from theorem 2.18 from the 4th edition. So I have taken one little result out of section 2.6 from the next edition, the 4th edition of Royden and Fitzpatrick. It's the 4th edition on which Fitzpatrick stepped in as a co-author. The claim is, there are disjoint sets of real numbers A and B for which the outer measure of A union B is strictly less than the outer measure of A plus the outer measure of B. Totally messed up. It shouldn't work like that, but it does, thanks to the axiom of choice, if you want to blame somebody about it. Here I'm saying I take this perfectly innocent set, I break it into 2 pieces, And when I add up the measures of outer measures of the two pieces, I get something bigger than when they were glued together. That shouldn't happen. But that's why we were so cautious about getting measurable sets, the Carey-Theodore splitting condition, and why we were so elated when we got countable additivity for Lebesgue measurable sets. Because countable additivity, finite additivity, doesn't even hold in general. Let's go through proof of that. It's actually not very long either. It says, well, suppose to the contrary, that the outer measure of A disjoint union B is the sum of the outer measures for every disjoint pair of sets A and B. Well, then, if I take any sets A and E, subsets of the reals, we can write set A as A intersect E, disjoint union A intersect E complement. And you know where we're going with this. Look, it reminds me of the Carey-Theodore splitting condition. If this holds for all subsets of reals, then I can write this outer measure as the sum of the outer measure of the first plus the outer measure of the second. But then that would mean every set of real numbers is measurable. So that contradicts the fact that set P is not measurable. I say it correctly. This would imply every set of real numbers is measurable, and we know non-measurable sets exist. We've constructed only one. More of that in a little while. I wonder how many non-measurable sets there are. Gives us a contradiction. So there must be some sets that do not satisfy the equality. Now, I guess it's in the realm of possibility. We could either greater than or less than. We already know by subadditivity we get less than or equal to, and we don't get the or equals to, as we just argued. So we must get the strict less than. So there exists a couple of sets out there where the outer measure of the disjoint union is strictly less than the sum of the outer measures. Yeah, you don't have finite additivity. That's a big shortcoming of Lebesgue measure, but it's an unavoidable shortcoming if you accept the axiom of choice. And you've got reasons to accept the axiom of choice. I'm about to say some belittling things about the axiom of choice. Well, it depends on your interpretation. We use the axiom of choice to show the existence of a non-measurable set. Is there another way to show the existence of a non-measurable set? If you'll read any other analysis book that constructs a non-measurable set, it'll use the axiom of choice just like we did. Details may differ. Axiom of choice will be there. If you read the 4th edition of Royden and Fitzpatrick, axiom of choice used to find a non-measurable set. So it's always the same construction. It's called Vitali's construction. We'll talk about him at the end of this section. Well, is there another way, not using the axiom of choice? No. Here's your reference on that. In 1964, Robert Solovay showed that we cannot prove that the sigma algebra of Lebesgue measurable sets doesn't equal the power set of the reals without the axiom of choice. The title of the paper was A Model of Set Theory in Which Every Set of Real Numbers is Lebesgue Measurable. Dates from 1970, I guess, his publication. This is going to be some pretty heavy, intense set theoretic stuff. It's also fairly lengthy for a research publication. I say this work lives in the realm of set theory. It involves manipulations of the axioms of set theory. Those are Mello-Frankel axioms of set theory with choice, the ZFC axioms, it's commonly called. There's a more readable paper out there. I found a copy of this one. Good luck reading it. It's on ResearchGate, so this may not always be out there, but it's out there now. Another reference is How Good is Lebesgue Measure from the Mathematical Intelligencer. It's only 5 pages long. If it's in the Math Intelligencer, it's going to be a fairly readable paper as well. But I couldn't find an online copy of that, or I would have put a link in here for that. What if we tried to live life without the axiom of choice then? Then we wouldn't have this problem. Now, here's some problems you would have. The axiom of choice is used in showing every vector space has a basis. The axiom of choice is used in showing every field has an algebraic closure, and some other things. Those are just the two that pop into my mind today. Yeah, the existence of a basis for a vector space is a pretty fundamentally important thing. So it has its role to play. It implies Lebesgue measure isn't defined on the power set of the reals. Okay, so Lebesgue measure isn't always countably additive. It's going to imply something called the Banach-Tarski paradox, which is also really just an additivity problem. Well, additivity problems are part of the landscape of real analysis, part of the landscape of measure theory. You don't have countable additivity. You don't even have finite additivity. Yeah, stay away from those sets. They're pretty exotic. If it takes the axiom of choice to create them, they're pretty exotic sets. I have a handful of homework exercises here that I would assign for this section. I'm not terribly interested in problem A and problem B. Let's read the statement of problem B, though. It says, show that if any set A has outer measure greater than 0, positive outer measure, then there is a non-measurable set, E, a subset of set A. All right, that's bad, because we're going to try to avoid these non-measurable sets. Looks like they're everywhere. You take any set of positive outer measure, it's got non-measurable subsets. So that means these non-measurable sets, they're everywhere. The only way we could create them was with the axiom of choice. I wonder how many there are. I wonder what the cardinality of the collection of non-measurable sets is. While we're at it, I wonder what the cardinality of the set of measurable sets is, the sigma algebra of Lebesgue measurable sets. What's the cardinality of that? It turns out to be bad news. We'll explore that in a supplement. There's lots and lots of measurable sets. There's Aleph 2 of them, if you accept the continuum hypothesis. Yeah, there's Aleph 2 non-measurable sets as well. So there's lots and lots of non-measurable sets. This construction is due to Giuseppe Vitali. There's a picture from him from the Mac Tutor History of Math archive. I've probably mentioned in the past. Excellent place for fairly deep history of math stuff. He's born in Italy in 1875. He attended the University of Bologna for 2 years and graduated from Scuola Normale Superiore in Pisa in 1899. Received a teaching diploma, taught secondary school from 1904 to 1923. And actually, that's some of his most productive years. 1923, he started at the University of Modena, moved to the University of Padua in 1925, became the chair of mathematics at the University of Bologna in 1930. Think of him as an analyst. He did his most significant work, it says here, between 1900 and 1908. Where we stand now, his most significant work is in 1905, he produces this non-measurable set. So this construction is called the Vitali construction of a non-measurable set. So it's named for Vitali. My guess is you've probably never heard of this chap before. You would encounter him in Real Analysis 1. You'd encounter him first in this, but he'll pop up again in a couple of other things. But this is called the Vitali construction that we went through. There's a reference on the original publication where the non-measurable set is established, 1905. Pretty good work considering Lebesgue comes out and publishes his Lebesgue measure and Lebesgue integration in it's 1902, isn't it? I think it's 1902 that's published. So this is fairly recently after the introduction of Lebesgue measure. He also characterized absolutely continuous functions as antiderivatives of Lebesgue integrable functions in 1905. We'll do that. It's our theorem 6.11. You've dealt with some absolute type stuff before. I don't think you've probably dealt with absolutely continuous functions before. We'll define that in chapter 6. He deals with Vitali coverings in 1908. We'll also see that somewhere in chapter 6. So big name chap relevant to this measure theory stuff. And a big name chap in terms of some of the integration theory to come as well when we look at Lebesgue integration. So there is a really weird result. What makes it weird, in my opinion, is the application of the axiom of choice. But there exist non-measurable sets. So every time we make a statement about Lebesgue integration on some particular sets, measurability is a concern. Non-measurable sets exist, and from that problem B I mentioned, and they're everywhere. Non-measurable sets are everywhere. You take any set of real numbers with positive outer measure, and within it are all these little non-measurable sets. So we'll always have to hypothesize things about measurability. When we define the Lebesgue integral, first we'll define measurable functions, and that measurable function stuff will be totally driven by the fact that we know there's all these non-measurable sets out there. So that's what lies in the near future, is shifting gears a little bit to dealing with measurable functions versus measurable sets. It's tied to measurable sets. It's the reason they're called measurable functions. And transitioning into looking at Lebesgue integrals. First, we'll look at a little bit more stuff from this chapter and look at some supplements as well. I still want to address that question. How many non-measurable sets are there? And for that matter, how many measurable sets are there? So we'll look at that soon as well. I will see you there. Have a nice day.